This is part 3 of a series of teaching videos to help you to understand covalent bonding and the formation of molecules. In this lesson, you must have a periodic table with you so that you can check the group numbers of the elements that are involved. Remember that the group number corresponds with the number of valence electrons of the element. And we will also be looking at how many bonds each element can make. In this lesson, we are going to look at the formation of ammonia, NH3. We're going to look at the formation of phosphine, PH3, and the formation of boron trifluoride, BF3. We will study the intramolecular bonds, the bonds inside the molecule, which are the covalent bonds because they are all nonmetals. We will be looking at the shapes of the molecules, and we will discuss whether the molecules as a whole are polar or non-polar molecules. So we will be looking at the bonds inside the molecule, the covalent bonds, are they polar or pure covalent? And then we're going to be looking at the molecule as a whole. Is it polar or non-polar? I will then briefly discuss the types of intermolecular forces between the molecules. And then we are going to put a bit of emphasis on drawing Lewis structures for these molecules, and then a few more on the next page. So I'm going to start with ammonia. Ammonia is made up of nitrogen and hydrogen, as the formula says, NH3. If you look on your periodic table, nitrogen is in group 5. Group 5 elements have 5 valence electrons. So nitrogen has 5 crosses around it to show the 5 valence electrons. So when I put the crosses there, I will start at the top, 1, 1, 1, 1, and then the 5th one. This is a lone pair, and then the 3 crosses that are on their own are bonding unpaired electrons. So the hydrogen atoms come along, each with a 1 valence electron. Hydrogen is in group 1. So one hydrogen orbital can overlap with one of the nitrogen unpaired electrons in an orbital, and that happens 3 times. So this is the Lewis structure for ammonia, and this is the Cooper structure for ammonia. And here is a 3D attempt at representing the ammonia molecule. I'm going to do phosphine and boron trifluoride's Lewis structures, and then we will look at the types of bonds between the elements that make up the molecules. Phosphorus is also in group 5. So it also has 5 valence electrons. I've done those in red. And then the 3 hydrogens, the same as in ammonia, will bond to the 3 unpaired electrons in the phosphorus atom. Here's the Cooper structure, and the molecule has the same shape as ammonia. I want you to notice that there are lone pairs, or there's 1 lone pair in the ammonia molecule and 1 lone pair in the phosphine molecule. These lone pairs push the bonding pairs away. This lone pair pushes the bonding pairs away. So we end up with a molecule that looks like this. The 3 lighter blobs are the hydrogen atoms. The blue one is the nitrogen atom. The hydrogen atoms are pushed towards the bottom. The same in the phosphine. The hydrogen atoms are pushed away towards the bottom. This shape is trigonal pyramidal. I do mention it on the table lower down, but we're not going to go there now. What I want you to notice here is the lone pairs and the lone pairs. Then in boron trifluoride, boron's valence electrons are the dots. There are 3 unpaired valence electrons in boron because boron is in group 3. So I spread them out evenly, 1, 2, 3. Then fluorine has got 7 valence electrons. Fluorine atoms make 1 bond. Boron makes 3 bonds. We always start with the element that makes the most bonds. So I'll start with boron as my central atom. Here I started with phosphorus as the central atom because phosphorus makes 3 bonds, nitrogen makes 3 bonds. So you do your Lewis structure starting with the element that makes the most bond. Boron makes 3 bonds, fluorine makes 1 bond. Fluorine has 7 valence electrons, so one of them will be unpaired. So there's the 7 crosses around fluorine, 7 crosses around fluorine, and 7 crosses around fluorine. What I need you to notice with this molecule, there are no lone pairs on the central atom. That is very important. Checking for lone pairs is very important. So the Cooper structure for boron trifluoride looks like this. The fluorines are evenly spaced because there are no lone pairs on the boron to push them away. So the molecule will look something like this. And this shape is trigonal planar. Now we're going to look at the types of covalent bonds in each of these 3 molecules. In ammonia, the electronegativity difference is 0,9. The electronegativity of nitrogen is 3 and that of hydrogen is 2,1. So the difference is 0,9. So the bonds are therefore polar covalent. Nitrogen has the greater electronegativity, so it's going to pull these shared electrons towards itself, making this molecule more negative on this side and more positive around where the hydrogens are. So these bonds are polar covalent bonds. We say they're polar covalent because the electronegativity difference is 0,9. This molecule is interesting because the electronegativity difference is 0. Phosphorus has an electronegativity of 2,1, and so does hydrogen. So these bonds are pure covalent because the phosphorus and the hydrogen have an equally strong pull on the shared electron pair. So we call that a pure covalent bond. The shared electrons spend equal amount of time between the phosphorus and the hydrogen atoms. So this molecule has pure covalent bonds inside. But I need you to notice that this lone pair causes this molecule to be asymmetrical. It's not a symmetrical molecule. So these lone pairs are negative electrons. They are going to make this molecule slightly more negative there and more positive around here where the hydrogens are. Okay, so this molecule is a dipole and this molecule is a dipole, even although it has pure covalent bonds. Then we get to the boron trifluoride. Here, your electronegativity difference is large. Fluorine has an electronegativity of 4. It's the highest electronegativity on the periodic table. Boron's electronegativity is 2, so the difference is 2. This is a very large difference in electronegativity. So these intramolecular covalent bonds are very polar covalent. The fluorine pulls the shared electron pairs very strongly. But because this molecule doesn't have lone pairs on the central atom, we are going to end up with a molecule that is positive in the center, but negative around the outside. So that is like looking at an orange, maybe a fruit orange, where the center of the orange is positive and the peel, the skin all around is negative. So this molecule of boron trifluoride does not have a positive side and a negative side. The main reason for that is because there are no lone pairs on the central atom. I'm going to go through these 3 very quickly by looking at the Lewis diagrams. This molecule has polar covalent bonds, and because of the lone pairs making it an asymmetrical molecule, it is a dipole. This molecule, the phosphine, has pure covalent bonds, but because of the lone pair pushing the bonding pairs away, it is also a dipole, but a weaker dipole than ammonia because the bonds are not polar covalent. They are pure covalent because the electronegativity difference is 0. This molecule of the 3 has the strongest polar covalent bonds. The polarity is the greatest in this molecule. But because there are no lone pairs on the boron, the molecule is completely symmetrical. There's no positive side and negative side. So the molecule as a whole is non-polar. I'm going to go to this third line of here in the table. It's a summary of what I've just said. The lone pair on the nitrogen pushes the bonding pairs away. It results in an asymmetrical molecule. A polar molecule, we can also call that a dipole. We have a polar molecule with polar covalent bonds. It's a polar molecule because it has a positive and a negative side. Phosphine. The lone pair on phosphorus pushes the bonding pairs away. It results in an asymmetrical molecule as well. It's a slightly polar molecule with pure covalent bonds. Pure covalent bonds because the electronegativity difference is 0. It is a weaker dipole than ammonia. The reason for that is because the bonds inside the molecule are pure covalent, whereas here they were polar covalent bonds. The boron trifluoride, there are no lone pairs on the central atom. That is extremely important. So there's no pushing away of bonding pairs. This results in a symmetrical molecule. We have a non-polar molecule. The molecule as a whole is non-polar, but it has very polar covalent bonds inside. So the intramolecular forces or bonds are very polar covalent bonds. The shapes, if we look at the shape of the ammonia, we call this trigonal pyramidal or trigonal pyramidal, your teacher might say, because the lone pairs push the bonding pairs away. The same with the phosphine, trigonal pyramidal, because the lone pairs push the bonding pairs away. Boron trifluoride, however, is trigonal planar. There are no lone pairs on the central atom, and all 4 atoms, the boron and the 3 fluorines, are all in one plane. The bond angles you might not need to know, but ammonia is 107 degrees between the hydrogens. So this is 107 degrees. Some textbooks and on the internet might say 107,3 or 107,5. And then you don't need to know the bond angle for phosphine. And the bond angle for boron trifluoride is 120 degrees. The angle between each of the fluorines, it's 360 divided by 3. So that's 120 degrees. Now we are going to look at the intermolecular forces of each of these 3, ammonia, phosphine, and boron trifluoride again. A quick summary: the molecules of ammonia are polar. The molecules of phosphine are slightly polar. And the molecules of boron trifluoride are completely non-polar. So their intermolecular forces are all different. The intermolecular forces between ammonia molecules are hydrogen bonds. Remember, water molecules, ammonia molecules, and hydrogen fluoride are the molecules that have hydrogen bonds as intermolecular forces. Please remember, these are bonds between molecules. On the previous page, we looked at the bonds inside the molecules. Hydrogen bonds are the strongest intermolecular forces. Phosphine is slightly polar, but there we have dipole-dipole van der Waals forces as intermolecular forces. And because it's a dipole, and the reason why these are hydrogen bonds and these are dipole-dipole is because nitrogen bonded to hydrogen, oxygen bonded to hydrogen, and fluorine bonded to hydrogen, those will result in hydrogen bonds between the molecules. Phosphine is a dipole, so therefore these are dipole-dipole intermolecular forces. They are weaker than the hydrogen bonds. Then boron trifluoride is a non-polar molecule because it's symmetrical. So non-polar molecules, all of them have London forces as the intermolecular forces. They are the weakest intermolecular forces. They are also a type of van der Waals force. They are also called dispersion forces, momentary dipoles, or induced dipole forces. But I think London forces is the term that is used the most. The boiling points are going to be affected by the strength of the intermolecular force. So the compound of the 3 that we're comparing, ammonia, which has the strongest intermolecular force, will have the highest boiling point. Ammonia will go from the liquid phase to the gas phase at negative 33.3 degrees Celsius. So it's a gas at room temperature. The boiling point of phosphine, because it's a weaker dipole and it also has weaker intermolecular forces, has a boiling point of negative 87.7 degrees Celsius, which is lower than that of ammonia. And then the non-polar molecule has the weakest intermolecular force, the London forces. It has the lowest boiling point, which is negative 100.3 degrees Celsius. A few more examples that we can look at, which have similar type of formula, is boron hydride or boron trihydride. Boron makes the 3 bonds. There, the 3 dots are the boron valence electrons. And then the 3 hydrogens bond to that with the overlapping of half-filled orbitals. This will be a non-polar molecule, so the intermolecular forces will also be London forces, weak intermolecular force. Boron trichloride is the same, very similar to boron trifluoride, also a non-polar molecule. And then boron, what bonded to hydrogen and chlorine, is just another option that I put in here. Boron, there are the 3 dots, the 3 valence electrons. So hydrogen's 1 electron can overlap with a 1 boron half-filled orbital, so can the chlorine and the other chlorine. This will be a polar molecule because chlorine has a higher electronegativity, so this bottom side will be more negative than the top. Just to get back to intermolecular forces and boiling points, etc., I will do another video on that with intermolecular forces and how boiling point and vapor pressure and so on is affected. Remember, the stronger the intermolecular force, the more energy is needed to overcome those intermolecular forces. Don't say to break the intermolecular forces. The stronger the intermolecular force, the more energy is needed to overcome those intermolecular forces. Therefore, the boiling point will be higher. So if I compare ammonia and boron trifluoride, the strongest and the weakest intermolecular force. Here, your intermolecular force, your London forces, are extremely weak. So it has a low boiling point because not much energy is needed to overcome those weak intermolecular forces. I will do more on this about the strength of intermolecular forces and how they affect vapor pressure and boiling points in an upcoming video.